Hi there. So in today's lecture, I would like to talk to you about the Poynting vector, intensity, and energy density for electromagnetic waves, and then how those things are all related to one another. Those quantities are all related to one another. Okay, so first a recap of some stuff that we've covered in previous lectures. We've already covered the equations for the energy density for electromagnetic waves, or electric fields and magnetic fields. So our energy density is an energy per unit volume. For an electric field, we define the energy density as U sub E is equal to 1/2 times epsilon naught times E squared. E is the magnitude of the electric field in any given region, and epsilon naught is the permittivity of free space. For the magnetic field, we defined the energy density U sub B as a similar equation, B squared divided by 2 mu naught. Here, B is the magnitude of the magnetic field in a given region, and mu naught is the permeability of free space. Now, also in a previous lecture, we related the electric and the magnetic field magnitudes. B is equal to E over C. So the magnetic field is equal to the electric field magnitude divided by the speed of light in a vacuum, 3 times 10 to the 8th meters per second. We also derived in a previous lecture exactly how C, the value of C, from the fundamental constants mu naught and epsilon naught. And that is that C is equal to 1 divided by the square root of mu naught epsilon naught. Now you can use these two equations here in the equations for the energy density and show that the magnitude of the magnetic field energy density and the electric field energy density is equal in electromagnetic waves. Okay? I'm going to let you do that for a homework problem probably. And what this means is that for light, in a given volume, the energy is shared equally by those two fields. Now we're going to define the Poynting vector, which is useful for some mathematical relationships and relationships between directions as well. The Poynting vector gives you the rate of flow of energy in an electromagnetic wave. That's what it does. This is important because electromagnetic waves do carry energy, and you need to understand as they propagate through space what direction that goes and how that goes so that you can understand how it might interact with objects that they might transfer that energy to. So here's the definition of the Poynting vector. The Poynting vector, S, is 1 over mu naught times the cross product of E and B. So 1 over mu naught E cross B, that's the Poynting vector. So you can see that that via the right-hand rule here shown in this graph, E cross B points along this x-axis because E points along the y-axis here, B points along the z-axis, and so you get S pointing in the x direction. Now that is, of course, the direction of propagation. So, and I'm sorry, but you have to do the pun, you just have to. The Poynting vector points in the direction of propagation. Okay, sorry, had to do it. Okay? Now, the Poynting vector's magnitude is not going to be constant in time. And this is because, of course, the electric and magnetic fields oscillate in time. So if you're doing a cross product of those things, then of course the product is oscillatory in time as well. Okay? Here is John Henry Poynting, who discovered and named and derived the Poynting vector. Okay? There you go. So the magnitude of the Poynting vector represents the rate at which energy flows through a unit surface area perpendicular to the direction of propagation. So, for example, if you had, as we'll do an example later in this lecture, if you have a laser beam traveling in this direction, then the Poynting vector defines the rate of energy through the area perpendicular to that laser beam flow. Okay? Now, it's a power per unit area. That's what the Poynting vector does. So if you think about the units on that, power, the SI unit of power is the watt, which is of course a joule per second, and the SI unit of area is the meter squared. So the units, the SI units for Poynting vector are watts per square meter. Right? Now what I'd like to do is mathematically relate the Poynting vector to the energy density and the intensity. And to do that, I'd like to do a little bit of math here. I hope you'll bear with me, okay? But it shows you how they arrive, first of all, at the equation for the Poynting vector and how it's mathematically related to the energy density. So here we go. The energy density for an electromagnetic wave, the total energy density, could be written as the sum of the energy densities from the electric and the magnetic fields. If you do that, then U, the energy density, the total energy density, is equal to 1/2 times epsilon naught times E squared plus 1/2 times B squared over mu naught. Okay? Now, we can write E squared, which is the magnitude of the electric field squared. We can write this as the dot product of the electric field with itself, so that E squared is E dot E. Of course, E squared is a scalar, but so is a dot product, right? So E squared is E dot E, and similarly, B squared would be B dot B, okay? Now, the energy density is not a power, so if we're going to relate the Poynting vector to the energy density, we're going to have to take a derivative, okay, with respect to time. And then that will give us the time rate of change of the energy density, right? Which is, of course, going to be the power density. So if I do that, then partial U with respect to t is what I need to do. Now, if I take the derivative with respect to time of this stuff on the right-hand side, then I can apply some mathematical rules here from calculus, okay? And I end up with 1/2 times epsilon naught, and here I have E dot E. So if I'm going to take the partial with respect to time of that, then it would look like this. Partial E with respect to t dotted with E plus E dotted with partial E with respect to t. Okay? And then I would do the similar thing for the dot products with the magnetic field for the B squared over here. Now, of course, A dot B equals B dot A. Okay? It doesn't matter in the order in a dot product, not like in a cross product. Okay? So partial E with respect to t dot E equals E dotted with partial E with respect to t. So if I sum those two things together, then I just get 2 times partial E with respect to t dotted with itself, E, right? So that means that my partial U with respect to t is going to equal to epsilon naught times partial E with respect to t dotted with E plus 1 over mu naught partial B with respect to t dotted with B, okay? The 2's cancel out because there's 2 of them. Now here I have some partial E with respect to t and partial B with respect to t. What I'm going to do is I'm going to use the Faraday's law and the Ampere-Maxwell law in empty space and plug in for those partials with respect to time. Now to remind you, in empty space, which means no currents, no current densities, no static charges, things like that, empty space, here I have the curl of E is equal to negative partial B with respect to t. That's 1. And the other equation would be the curl of B is equal to mu naught epsilon naught times partial E with respect to t. So I've got my partial E with respect to t here, my partial B with respect to t. I'm going to plug in for those in my partial U with respect to t. Ready to go? All right. Rearranging those equations, Faraday's law and the Ampere-Maxwell law, to just be partial E with respect to t and partial B with respect to t on one side, and then plugging those relationships in to my partial U with respect to t expression, I end up with partial U with respect to t is equal to epsilon naught divided by mu naught epsilon naught times curl of B dotted with E. Now plus 1 over mu naught times the negative curl of E dotted with B. So yet again, I'm just using those equations up there and substituting in. Please remember, if at any time you need to stop, pause the video, and make sure you can keep up with the math, definitely do that. Okay, so you might be looking at this expression for partial U with respect to t and be thinking to yourself, now that's a hot mess. I don't want anything to do with that, okay? But it's actually not too bad because there's a vector identity from vector calculus, if you remember your Calc 3, that you might be familiar with, okay? Now, I'm not going to prove it. I'm just going to use it, okay? If I use this vector identity right here, the divergence of C cross D, so del dot C cross D, it's equal to the curl of C dotted with D minus the curl of D dotted with C, okay? So I just left these things C and D in terms of it's true for all vectors C and D, okay? So it's just generic. But you can see that if you let C go to B, right? You let C go to B and D go to E, then you can see that we have a match here. We have a match. Now we have a match here especially because this constant epsilon naught over mu naught epsilon naught, the epsilons cancel out, And I'm just left with 1 over mu naught, which I can pull out front, okay? And that just leaves my curls in there, okay? So I'm going to use that vector identity and plug in for it here to simplify my expression a little bit. So when I do that, I'm going to end up with partial u with respect to t is equal to 1 over mu naught times del dot b cross e. Okay, so that looks a lot nicer, right? It's much shorter anyway. Short is good. But it doesn't look like my Poynting vector. My Poynting vector is e cross b, but never fear, right? The cross product, it's not commutative. It doesn't commute. So a cross b doesn't equal b cross a. But a cross b does equal minus b cross a, right? So what I can do is I can say, instead of b cross e, which doesn't look like my Poynting vector, I'm going to do e cross b and then just pull a minus sign out front. Okay? So that's what I've done here. So now I have partial u with respect to t is equal to negative 1 over mu naught del dot e cross b. Okay? Now 1 over mu naught e cross b, that's my Poynting vector. So, since that's the case, that means that partial u with respect to t is equal to negative del dot s. And I'm done. I've got a mathematical relationship here now that relates my energy density u to my Poynting vector s. So let's talk about it for just a second. Partial u with respect to t is the time rate of change of the energy per unit volume. Okay? So it's a power density. Okay? Now, my Poynting vector here, you can see here that it's the gradient, the negative divergence, of s. Okay? Now, remember, s was a power per unit area. But then I take a derivative of that, and when I take a derivative of a power per unit area, I get a power per unit volume. So you can see that these two things are equal. Right? Now, what does this tell us? This is actually a continuity equation. That's what it is. It's an energy continuity equation, which really means that it's an energy conservation equation. Okay? So this is an energy conservation equation. It's telling us, and I'm going to quote Purcell and Morin here, energy can't just disappear. If the energy in a given region decreases, right, then it must be the case that the energy flowed out of that region and into another region. So in other words, let's think about what happens with our electric and magnetic field as it propagates through space. You've got this oscillating electromagnetic field and it's also propagating. So in a given region of space, you might have your electric field magnitude go to 0, right? But it pops up in another place, okay? And so the energy has moved away, all right? So that's what's going on there. Okay. Now, Poynting vectors are all well and good, but usually people like to think in terms of intensities, okay? So it turns out that the wave intensity, which I'll call I, it's actually a funny I looking here. It looks a little bit like a J, but that's supposed to be a curly I, okay, according to Microsoft's equation editor. Sorry. Okay, so this is a wave intensity, and it's the time average of S, okay? So it's the time average of the Poynting vector over one or more cycles. Now, if you think about it, this actually makes sense. Remember, S varies in time, okay? The value of your Poynting vector is not the same at any given time. It oscillates. And so, really, you don't want to know what the Poynting vector is at any given time so much. Really, you want to know what the average value of it is to know how much energy in general is going on. So it makes sense that you'd be more interested in the intensity. Now, we define as in physics an intensity as a power divided by an area. Okay, so that's a power over an area. And so that squares very well with what we know about our Poynting vector, right, which is a power over an area. All right? Okay, so I told you that the intensity is the time average of the Poynting vector. Let me prove it. Here, S is equal to 1 over mu naught E cross B. Now, I don't want to do cross product stuff right now. I don't feel like it. No. So what I'm going to do is instead I'm going to find the magnitude of S, okay? So if I take the magnitude of my Poynting vector, that's going to be 1 over mu naught times the magnitude of my electric field times the magnitude of my magnetic field times the sine of the angle in between them. Well, the electric field and the magnetic field are always perpendicular to one another in light. So the sine of that angle would be 1. So there you go. So my magnitude of S is magnitude E, magnitude B over mu naught. Now, I'd rather just deal with one equation. I don't want to multiply an electric field times a magnetic field when I'm doing my integral, so I'm not gonna. I'm just gonna write the magnitude of E in terms of the magnitude of B and plug in for that. Luckily, I know what that is. They're related to one another by the speed of light. So E is equal to CB. Okay? So I chose here to plug in for E. So I plugged in CB for E. So that means that I've got for my Poynting vector magnitude C times B squared over mu naught. Okay? Now, B, like I said, is not always the same thing. It oscillates in time. I'm going to pick the simplest possible sinusoidal function that I can in order to simulate this, but it is generally true for any wave function. So B of t, I'm just going to write as a cosine function. So I'm going to say that B of t is equal to B naught times cosine of kx minus omega t. Like I said, I took the simplest way out I could. Now what I need to do is I need to do the time average of that. So in order to do that, what I'm going to do is I'm going to integrate over one period, okay, for C B squared over mu naught. I'm going to integrate over one period of that with respect to time. Now that gives me a cosine squared. And I don't like cosine squares in my integral, so I'm going to use a trig identity instead to get rid of it. So the trig identity I'm going to use is cosine squared x is equal to 1 plus cosine of 2x over 2. So plugging in for that, the time average of my Poynting vector, integral over 0 to t, big T, which is one period, c over mu naught times b naught squared, times 1/2 plus 1/2 cosine 2 kx minus omega t integrated over dt. All right. Now, when I integrate the 1/2 part, I get 1/2 t, which I then evaluate from 0 to t, which gives me 1/2 t. Okay, good, where t is my period. When I integrate a cosine, I get a sine, okay? Now, it's true for all cosine and sine functions that if you integrate over one period, that let's say that you start on the crest of one wave and you integrate over one period, you end up on the crest of the other, okay? So neighboring crests. And then these have the same value, so you subtract them and they go to 0. So it's always true that this bit right here, if you integrate over just one period, is going to give you 0, okay? Another way to think of it is, of course, the sine function is periodic, and let's say that you pick some random point like x equal to 0, then when you evaluate your time, you're going to have sine of 2 pi minus sine of 0, and both of those things are 0, so there you go, all right? Either way, I end up with, for my average value of s here, c b naught squared t over 2 mu naught. Now that's equal to the time average of my Poynting vector here, which would be s average times my period. So my periods cancel out. And that leaves me with S average is equal to C B naught squared over 2 mu naught. Okay? Now I could put that in terms of my electric field, my magnetic field, or both. So here I've shown you the expression for S average for C B naught squared over 2 mu naught. I could use B naught is equal to E over C and plug in for that. And then I end up with S average is equal to E naught squared over 2C mu naught. Okay? Now, if you're looking at that and you're thinking, gee whiz, that looks super familiar, right? Doesn't that look just like my energy density but with a C multiplied by it? Well, yes, it does, okay? So it turns out that the intensity, which is equal to the average value of my Poynting vector, is going to be C times my average energy density. Who'd have thunk it, right? Okay. So that's how these things are all related to one another. The intensity is equal to the average value of the Poynting vector. Remember that in intensity we want an average value of power over area, not in some instant in time. So that's why we have to take the average value of S. And then that's S average is going to equal to C times U average. Okay? All right, let's do an example problem. Remember that the thing that the Poynting vector and the energy density and all this stuff does nicely for you is it relates the electric field magnitude at any given point to the intensity and power and things like that that you can measure. So here we go. The maximum electric field strength in air is 3 megavolts per meter. If you have a stronger electric field than that, then it'll ionize the air and create a spark, lightning. So what's the max power that can be delivered by a 1 centimeter diameter laser beam propagating through the air? Obviously, you don't want your laser to make lightning. That would be bad. Okay, so here we go. We're going to use the average value of our Poynting vector. S average is equal to E naught squared over 2C mu naught. okay? And then that's going to equal to our intensity. Remember, our intensity is a power per unit area, okay? Now, in this case, we have a laser beam going this way, okay? Now, if you look down the pike of the laser beam, they're circular, right? The cross-sectional area is a circle. And so the power divided by the area that you're going to be dividing by is the area of that circle that the laser beam has. So that's pi r squared. Now, they give us the diameter, okay? So that's a little tricky. But remember that the radius is half the diameter. Okay, so plugging in for all of those things, E naught is going to be the maximum electric field strength. We're going to see how much we can dial it up, how much power we can get before we max it out and make a spark. So plugging in for the max electric field strength that we can have, we want to keep it under that, then we would have 3 times 10 to the 6th volts per meter, and we would square that. And then we would divide that by 2c mu naught. Now c is the constant, 3 times 10 to the 8th meters per second, the speed of light in a vacuum. And mu naught is the permeability free space, which in SI units is 4 pi times 10 to the minus 7. So plugging those numbers in, we then set that equal to the power divided by the area, which is pi times 0.005 meters squared. We would then solve for the power. And when we get that, we get 9.4 times 10 to the 5th watts, which would be 940 kilowatts, right? Seems pretty impressive. All right. I hope you enjoyed that and understood it. Remember, at any time, pause those videos if you get confused, and I'll see you around.